Okay.
That's my notable achievement.
Okay. But you can hear Pete on a regular to irregular basis on the Solder Smoke podcast, and you update your blog quite a bit with projects that you're working on.
Yeah.
What's the address for that?
N6QW.blogspot.com.
Okay, great. Oh,
Are we ready to start?
we're going. Let's go ahead.
Okay, cool. Well, first off, I'd like to thank the G-QRP Club for the opportunity to talk a little bit about some of my favorite subjects. And I also want to share that my XYL is really happy that I'm presenting today, because I combed my hair, I shaved, and I got rid of the t-shirt that says COVID cure, drink a lot of beer. So she's happy that I'm not wearing that today. But the first slide here is a photograph of one of the projects I built that I want to talk a little bit about, the KWM4. And also importantly is a URL address. Essentially, I'm going to talk about homebrewing an SSB transceiver, but there's a whole series of web pages that are dedicated to the actual construction. So there are a lot of links in there, shows photographs, circuit diagrams, explanation of what the circuits do and how they all connect together. And so just jot that down. You'll see it throughout the presentation, and it's essentially mycallsign.com /gqrp.html. So you're going to see that over and over again, but that's where all the meat is if you actually want to build one. So next slide, Nick. I guess I shouldn't say roll your own rig, because that kind of dates me. I guess I should be saying DIY your own rig. And I guess the thing that I really enjoy doing is when having a QSO is to really be able to say the station at the other end, the rig on this end is homebrew. I do have commercial equipment, but by and large, I tend to use all my homebrew equipment. And that not only the pleasure of the QSO, but also the opportunity to use equipment that I designed and built myself. Next slide. You know, a bit of history here. Early on, at least when I started back in the late 50s, rigs were two big boxes, a big receiver and a big transmitter. And I remember the DX100B I had, you got a hernia if you tried to move that around the table. And now we have transceivers that fit in the palm of your hand. And we're really enjoying the benefit of the technology that has moved along here. And the transceivers are modular in their construction, and upgrades are simplified. So indeed, we live in a great time. Next slide. Here we go.
Sorry about that. It's decided to
hang up.
Yeah, it's decided to hang on me for some reason. There we go.
There we go. Now, technology has served us well. Today, we hear people talk about homebrew rigs having Arduinos or RPi4s, the PLL, the SI5351. And these are essentially like electronic Lego box. You just connect them together, and the interfaces are pretty compatible. So there's not a lot of effort to connect these blocks. And also today, we see a technology shift from analog to digital. I can remember struggling trying to build analog VFOs that would be tamed, and now you build them in digital and you don't worry about that. And also there's a technology shift from hardware-defined radios to software-defined radios. So the wave of the future is SDR. Next slide. Now, the new technology opens up a whole new realm of possibilities. First of the new hardware is user-friendly, in large brought about by the reflectors. I mean, you can find reflectors for Raspberry Pi, microBitX, what have you, and a good opportunity to get plugged into the worldwide community and find out a lot of information or get questions answered. And the new technology is modular, so there's rapid prototyping. I remember the days I built a 13-tube transceiver, and I spent a lot of time bashing metal. Now you just connect circuit boards. We also have the opportunity to test as you go, so that you don't build the whole radio, turn it on, and it's a giant smoke test. you can test the individual modules as you go along. And also, many of our projects today have BITE, built-in test equipment. For instance, most of the transceivers that I build today, I take advantage of the Arduino and generate a tone, create a pulse tone. And when I want to test the rig on the air, I just punch a button and it produces a 10-second pulse tone. And so it's essentially built-in test equipment. We also have new instruments, new test instruments. Who doesn't have a nano VNA in their shack? 50, 60 bucks, you can have one in the palm of your hand, and a $300 100 megahertz 2-channel digital storage oscilloscope. I mean, it's kind of amazing. Technology like that 10 years ago was thousands of dollars. Now it's in the hundreds of dollars. Next slide. So, okay, where's this headed? Today, I want to talk about homebrewing an SSB transceiver, but again, here's that URL that I mentioned. And I spent a little time trying to detail this project so that you have enough that if you follow it, you'll be able to successfully build a single sideband transceiver. Now, while today's focus is hardware-defined radios, the future is SDR, and I'll mention a little bit about that later on in the presentation. Next slide. Here we have a simple SSB. It has 9 common devices. And again, this is what is featured on that website that the URL is below. And it's the 9 common devices are nothing exotic. 2 N3904s, 2 N3906s, a couple 2 N2219s. We've got an IRF 510 in there, and one IC, an LM386. So you don't have to put a lot of hardware in there to achieve some really excellent results. Next slide. Here's another example. This one is 2 N6QWs doing the heavy lifting. And for those who are G-QRP members and subscribe to the Sprat, this is a project that it was written up here about a year ago. This has got 2 VFOs, color TFT display, and the heavy lifting is 2 NE602s. That's pretty much the bulk of the transceiver. Next slide. Here I wanted to test some concepts of using the OLED displays, and this is a pretty small transceiver. We're talking about something that's 4 by 6 by 2, 5 watts, 20 meters, and that nice little OLED display right in the middle sure catches your eye. Now we move on, next slide, to the bazaar. I managed to get a plastic champagne bottle filled with candies. And I looked at that and I said, why couldn't I build a transceiver inside of a bottle? And this is a working transceiver, and I was able to drill the Lexan plastic pretty easily. And you too need to have one of these sitting on your shelf. It gets a lot of comments. Next slide. This is perhaps one of the most complex projects that I've ever undertaken, called the KWM4. And the reason it's called the KWM4 is I looked at the Collins KWM2 and I'm saying, why couldn't I build a solid state version of that? And it has a 455 kilohertz mechanical filter. It is dual conversion. The only band it doesn't operate on is 30 meters. And the reason is the first IF is at 10.7 megahertz, which would be too close to the 30 meter band. But this one also has a keypad, and I'm deeply indebted to Ron Taylor, G4GXO, who wrote some code for me to have a PIC 16F84 that's behind that keypad. So I can manually tune that transceiver right from the keypad. So lots of technology here, and kind of cool to be able to just push a button and it'll tune up, push a button, it'll tune down. Next slide. We were discussing early on when this first started, and I said, you know, I always start with a noodling process. The last thing I do is turn on the soldering iron. I try to think my way through building a single sideband transceiver, and I wanted to just kind of briefly review what are some of the topologies for a filter type rig, and what are the modules. And it's important that you identify these modules, because that enables you to see how things go together and you can identify common elements. And when we're able to focus on these common elements, then we can take a separate receiver and transmitter and build them into a transceiver. Next slide. Now, there are many topologies for single sideband transceivers. And the three listed below are pretty much dealing with the filter type rig. And of course, you'd have phasing rigs, which wouldn't have a filter in it. And you also have the SDR, which does not have a crystal filter in it. But essentially, the single pass is that signals pass in a single direction through the IF module. The bilateral, which many are familiar with the BitX and the micro BitX, actually pass signals both directions. And there's what I call a switch filter, and a very clever design from two hams in Spain came up with a design called the Pilgrim, the Peregrino, and they actually physically switched the filter between ports on two N6QW. So that was the first time I've ever seen that. And 84 parts, and it's a whole transceiver, so it just sort of blows your mind. But depending upon what topology you select, involves things like signal routing, minimum part count, and of course, cost. More exotic, more cost. I built all three approaches, and they all have some pluses and minuses to them. Certain cases, like the switch filter, minimum part count, if you're going to take this thing portable on say a hike or something like that, parts and weight really count. So maybe that is a better approach than something where it has a lot more exotic parts. Next slide, please. We want to look here at what I call the single pass topology. Essentially, the IF module has signals that pass through it in one direction. In the receive mode, we have a receiver mixer, and the resultant signal from the receiver mixer passes through the IF module into the product detector. Now, when we hit the TR switch, what happens is that module is then switched from the receiver mixer to the balance modulator, and from the product detector to the transmit mixer. But in all cases, we're essentially have a single pass, a single direction of the signal, that it either goes one way from the receiver mixer to the product detector, or again, a single direction from the balance modulator to the transmit mixer. Next slide. If we look at a generic modern single conversion, single sideband CW receiver stage, we see the arrows are all starting up in the upper left-hand corner, and as they pass through the various blocks, ultimately end up in the lower right-hand corner with the audio amplifier. And the colored blocks are identifying the potential for stages that could be common elements. So essentially, we go through low-pass filter, antenna, RF amplifier, bandpass filter, mixer stage, the IF amp module, and then we have a carrier oscillator, inject a signal in the product detector, and out comes the audio amplifier. So that's a kind of a generic, maybe there's little twizzles on this, but just think of it in terms of those elements. Next slide. Now, a transmitter actually reverses the direction. We have a microphone amplifier into a balance modulator, again, a carrier oscillator. We have the IF amplifier block. We got a transmit mixer, local oscillator, bandpass filter, and onto the antenna. So in the receiver case, it was starting in the upper left-hand corner and proceeding down to the right-hand corner. In the transmit case, it starts in the right-hand corner and goes singular direction to the antenna. Next slide. Now, there's some common elements. If we look at some double balance mixers, which can be used as transmit and receive mixers, and also as balance modulators and product detectors, 2 devices can do 4 jobs. So that's a good common element where you can have 2 simple devices, in some cases 3 terminal devices that enable you to use them both on transmit and receive. I want to talk a little bit about the IF module. Can be as simple as 4 transistors and bilateral. And the importance of this is that we're not switching the LO and BFO. They're not hot switched. I once built a transceiver that switched the local oscillator between the receiver mixer and the transmit mixer. It was physically switched. And I could never get that on the same frequency because the loading of the receiver mixer was different from the transmit mixer. And no matter what I did, I could not keep that on the same frequency because the change in the load was reflected back on a frequency shift in the VFO. So when you use the double balance mixers, you don't have that problem because you're not switching the LO and BFO. And in many cases, we can do double duty. We can have modules, for instance, some amplifier circuits, and even filter networks like bandpass filters can be used both on transmit receive, and the same thing for low pass filters. they're bidirectional by nature. So that makes them kind of nice in putting our transceiver together. Next slide. Again, this is what we had with the single pass, just to keep in mind how the signal routes through there. We're switching the IF module between the elements used on receive to the elements used on transmit. And so if we can combine some modules, next slide, we can have bilateral circuitry. So if we take our ADE1, and I happen to use that because they're pretty low cost today. As a matter of fact, just recently, Mauser started carrying the ADE1 for about less than $5 a pop on a single unit. So the ADE1 can be a balanced modulator, a product detector, and a carrier oscillator is connected to it at all times. If we come up with a bilateral IF amplifier circuit, then it can be used both on transmit and receive. That gets dumped into another ADE1, which now is either a receiver mixer or transmit mixer, and the local oscillator is always connected to that, so there's no change in load. And the bandpass filter is bidirectional. And I came up with a little design for a bidirectional amp that on receive is the receiver RF amp, and on transmit is the transmit pre-driver. So we have a bilateral circuit here that we certainly eliminated a lot of those blocks, and it's just a matter of how we route the signal through all the various blocks. It depends upon whether it's receive or transmit. Next slide. What are the benefits? Well, benefits: reduced part count, lower cost, and more compact equipment. We're not hot switching the LO and BFO. All the circuits are designed for Z in, Z out of 50 ohms. We can optimize stage gains, and we could also do a lot of physical isolation. I tend to build a lot of circuits in modules on circuit boards and kind of just screw them down to the top of the workbench. And boy, that'll work kind of okay, but when you put them all in a small little box, you got to worry about physical isolation. The other thing too is when you're minimizing the part count and minimizing the number of modules, the fabrication process is minimized. I mentioned that 13 tube transceiver I built. It took me months to drill all the holes and mount all the tube sockets and how to route everything. So today's construction techniques really enable you to go from a design to a finished product in a much shorter time. Next slide. Now here's a block diagram of the simple SSB, and essentially it's one band. There's two VFOs. It's upper and lower sideband selectable. I happen to have an Uno R3, so the Arduino Uno R3, kind of big in comparison to the Nano or Pro Mini, but it existed and I used it. I have a 16:4 LCD at 5 watts, and I've used this on FT8 and Whisper with a little external adapter I have. So essentially, we have an Arduino supplies the LO and BFO, and that gets dumped either into the receiver or transmit mixer stage or to the product detector balance modulator. And into the product detector and balance modulator, the same port takes the microphone amp or audio amp. The same port, it's possible to connect them together without interference, and you just power one on or power the other off. Bandpass filter is a common element, and as I said, I came up with the 2N2219 bidirectional amplifier. Now, in the original, and you'll see this on the website, the original design is I developed two J310s so they can simulate 40673 dual gate MOSFET. So on the website is both designs, but that uses a lot more components than the 2N2219. And I have since come up with a design that the bidirectional amplifier you see in the yellow block is exactly the same circuit as the driver. So it's minimum part count. There's only one change in an emitter resistor. So again, a little simplification, but both designs are shown on the website. Next slide. The heart of the simple SSB transceiver project is a bilateral IF module. Thank you, Plessy. It has 4 low-cost transistors. It's wideband, moderate gain at 8 volts DC. This is literally bulletproof. And for those who always want to know, where did this come from? Get out your copy of EMRFD figure 6.110. Therefore, it passes the smell test. There's a good rationale to use this. If it appeared in EMFRD, then it's got to be gold. And Wes Hayward mentions that this thing is good to about 40 megahertz and about 17 dB gain. Now, they they use 6 volts DC, but I have upped it to 8 volts DC with no ill effects and slightly more gain. And Wes does mention that if you go to like 12 volts, you got to do some other things because just the circuit components that are being used, you're going to run those things pretty hot if you're running at 12 volts. So 8 volts is okay, but 6 volts is, you'll see the design factor. Next slide. Here we have, this is kind of an eye chart, but there are 2 of these bilateral circuits with the 2N3904, 2N3906 on either side of a G-QRP club filter. Now, I use the club filter in a lot of my projects, and they're getting scarce as hen's teeth. I understand there's just a few in the bin, so if you're so inclined to build this project, get your order in for a filter and contact Graham Firth because there aren't many left. Now, there's some alternatives to that. I have built the same circuit using INRAD model 351, which is a 9 megahertz filter. And the only difference is it's the G-QRP filter is 500 ohms, and you do have to use matching transformers. And since we're going 50 to 500, simple matching is 19 turns, and you tap it to 6 turns. So 6 turns is 36, 19 is 361, 36 into 361 is 10 to 1. So you got to step up from 50 to 500. Now the INRAD filter is 200 ohms, and that's a 4 to 1. And I detail in the website how to do that. And even still, INRAD has lists those currently out of stock, but I don't think that there's not a case that they're not going to be selling them. I think they're just temporarily out of stock, and I want to verify that. But I have used the 351. As a matter of fact, the radio in the bottle has got the model 351 in it. Next slide. Now, this slide has 2 purposes. One is to show you how I use graph paper. And this is just 1/2 of the bilateral IF module with the 2N3906, 2N3904. And I happen to have a CNC mill. And there are a lot of CNC mills that you can acquire for like $200 to $300. And I know I have friends who have purchased these, and they work just fine. And what I do with the graph paper is lay out the circuit, and then you can count the squares, and that becomes the coordinates that you input for the design that ultimately results in the G code that you can cut the circuit with. Now, just to see how the circuit works and how you switch from transmit to receive, if you look at the 2N3904, which is the lower transistor there, the input, it's an input output and output input. In the input mode, where you have the 100 ohm resistor in the emitter of the 2N3904, that's grounded. So that means that 2N3904, which is the NPN, is hot. So the signal is going to pass from left through the 2N3904 to the output. Now, when you switch that one connection from ground to 8 volts, and by the way, in the receive, where it's grounded, essentially the emitter of the PNP, the 2N3906, is at ground, so it doesn't conduct. So you get nothing through that part of the circuit. Now, immediately when you switch it with a little small relay and add 8 volts in the transmit side of this, what happens is you're back biasing the 2N3904, so that doesn't conduct, but now you're applying 8 volts to the emitter of the 2N3906, and that's conducting. So the signal now goes from the right side to the left side. So the output becomes the input, and the input now becomes the output. So just with a simple change between ground and 8 volts, this Plessey circuit can act in the bilateral mode. And I have built this in surface mount. I have built this in through hole. Surface mount gets a little bit tricky because I suffer from a malady called FFS, which is fat finger syndrome. And my fat fingers have a real tough time holding down those parts and gently soldering the parts to a board. But this is basically how the circuit works. And I want to go into a little more detail on one part of the circuit, the PNP part. Next slide. And that is LT Spice. You know, you can't really do any home brewing today unless you avail yourself of some of the new technology that's available. And I'm a firm believer in LT Spice, which is a free download from Linear Technology. It's circuit simulation where you can go through and simulate circuits, and it saves the soldering iron. The last thing you do is turn on the soldering iron. First thing you do is do a lot of noodling and use the tools that are available to you. Now, a couple other devices, the Antuino and the Nano VNA, if you're building networks and filters, you can check them. You can check them once you've designed them in LT Spice and you see the circuit simulation and say that looks okay. And when you actually build the hardware, you can physically check to see that what you've built really works. And as a matter of fact, sometimes it's a little, you find out some interesting factors. For instance, you can design a network in LT Spice and you get a plot that says, oh, that's perfect. And then you actually build it. And next thing you know, you look and it doesn't match the plot in LT Spice. And what you find is it's the circuit components and how good of, and I want to mention that a little bit later, how good the circuits are. Like it may require 100 picofarad capacitor in the circuit. Well, if you're using 30% capacitors, which a lot of this very inexpensive stuff coming from China is, it could be 70 or it could be 120. So that's going to shift your network. So that's why it's really important that once you simulate it, you know the values are good for the nominal value. Once you build it, then you need to check it to make sure that in fact it's doing what it's supposed to be doing. We also have the 100 megahertz digital storage oscilloscope. Many of them come complete with fast Fourier transform analysis. That's amazing when you check out a network and you look on the scope, is the second harmonic really down 45 dB? So that's kind of important. The other thing is don't overlook homebrewing simple RF signal generators. Take that 809850 that you're no longer using because you moved over to an SI 5351 and build yourself a little signal generator with a little LCD and there you go. You'll be able to check out your circuits. Again, the last thing you do is turn on the soldering iron. Next slide, please. Okay, here's the PNP portion of the bilateral amp. And interestingly enough, C1, which you see there connected to the emitter, that emitter bypass cap, that plays an important role. Now in the Plessy design, that thing is 100 nanofarad, and I simulated that. And I saw something interesting that you got a lot of gain on the low end of the spectrum, but on the high end, out at 30 megahertz, it was a 3 dB drop. That means what's going to happen is when you get to 30 megahertz, you're going to you're at the half power point. So if you need a lot of drive at 30 megahertz, you just lost half your drive of what you see at 3.5. So I simulated a change of C1 from 100 nanofarad to 4.7, and I wanted to see what that effect is. Now, for those of you that have solid state design for the radio amateur, which I cut my teeth on, Wes Hayward talks about the effect of capacitors on the emitter, and you see that very definitely in this case. And I changed it to 4.7 nanofarad because of the next slide. And there you look and you see at the low end at 3.5 megahertz, you don't get the gain that you'd get with the 100, but there is a drop, but the drop is not as dramatic as you see with the 100 in there. The 4.7 drops at about 2 dB, so you're not, if you're really critical on the amount of drive you need out at 30 megahertz, then you may want to change that capacitor. Now, what is really interesting with the availability of LT Spice, this just plots the output. It is possible to plot the output versus the input. And the thing that's interesting, when you run that curve and you look at the output versus the input, and there's functionality in the LT Spice that lets you do that, you get a flat curve. So obviously, when they were designing the circuit at Plessy, they said, what gives us a flat gain from 2 to 30 megahertz? Well, all it's telling you is that 30 megahertz, it requires less drive to drive that circuit to give you the same amount of gain that you would get at 3 megahertz. Now that's all well and good, but that just relates to the circuit itself, the input versus the output. What's important is how much physical real output are you getting on the output stage. So I don't want to belabor this, but I'm just saying you have available to you the opportunity to use analytical tools to see what the impact of circuit changes are. The other desirable side of having LT Spice, you look in the junk box and you need a 3.3K resistor for the circuit. And you look in there and all you got is a 2.7. So, you know, the first tendency is to say, well, just put it in there. It's close. It's close enough for government work. But it actually may be impacting your circuit. So using LT Spice lets you verify there's indeed a change from 3.3 to 2.7 have any impact. In many cases it doesn't. Sometimes it does. So that's really important to having the tool. Next slide, please. What else do we need? We have the IF module. And again, all this is detailed in the website. The critical modules use the double balance mixer, so there's no adjustment, no tuning. The bandpass filters and the low pass filter, again, I want to mention using quality parts for the capacitors. The ceramic on glass or the silver mica are really important, and measure them. Measure them first to make sure the values are correct. I bought a bag of, let's see, it was 1,200 capacitors from China for $8. I said, man, what a deal. This is less than a penny a piece. Well, let me tell you, they're absolutely worthless, because none of the values marked on the capacitors are what the value of the capacitors are. Now you could sit and measure all 1,200, and yeah, what a bargain at $8, but they're not going to do you very well in those networks. And it's really important when you're building bandpass filters and low pass filters. This prevents you from getting in trouble and having out of band signals. So I can't stress enough to use quality parts, especially the capacitors, because those networks are dependent upon those capacitors. Now, the bidirectional amplifier and transmit driver are the same circuit, and the final amplifier is an IR510. Of course, we have the Arduino SI5351, display, encoder, the encoder, TR relays, and voltage regulators. Now, I did something on the simple SSB on that website URL that you have. I don't provide the code for the Arduino, and that was just so I know how many people are actually building this. So all you do is send me an email, qrz.com email address, and I'll send you the files that you need, all the files that you need to make the Arduino work. You know, work with a Uno or a Nano or a Pro Mini. You just need to make sure you have the right device when you go to load the code. So you'll see that in there. I mentioned it, but that was a way for me to know how many people are building this. Next slide. This is a 3-section bandpass filter, and I want to share with you an interesting situation that occurred as a result of building this transceiver. Typically, I use a 2-section bandpass filter, and I came up using LT Spice with a 2-section bandpass filter that used 5 little ceramic trimmers, the requisite number of inductors, 2 inductors. And I found that if you used 0 to 50 picofarad, you could, just by the addition of 2 150 picofarad capacitors across the tanks, you could either tune that thing up for 20 meters or 40 meters. So in terms of stocking of parts, if you just got the stock of parts, essentially just with the addition of 250 picofarad capacitors, you essentially could either convert it to 40 meters or you lift the capacitors off and have 20 meters and just retune the caps. And that worked very, very well, except one short side of that. And the short side of that is it tends to tune up on the single sideband portion of the bands. So the 2-section filter does extremely well from 7.15 to 7.3, or, you know, from 14.15 to 14.35. So it works really well there. But if you want to use FT8, you suddenly found that the output dropped off the cliff because that network was pretty narrow. It was flat. It was a flat network, but it was pretty narrow. So then I looked at, thank God for Farhan, the BitX design, and he has a 3-section filter in there. And I just essentially lifted that filter right out of the BitX, and I just scaled the components In this case, I just scaled the components so that it works on 20 meters. And these values here, and they're included on the website, will give you the 20 meter and the 40 meter bandpass filter. And these things are like 2 megahertz wide. So it'll tune like from about 6 to 8 on 40 meters, and it tunes like 13 through 15 on 20 meters. And that's kind of nice, and it's flat. And it's really nice because then you don't have to worry about if you're trying to do FT8 that suddenly your power is going to drop off. Now, in the lower part of this slide is a 3-section 20-meter bandpass filter, actual plot using the Nano VNA. That looks really good. I mean, I was impressed when I ran that network produces that kind of waveform, and it's got nice roll off on the high end and the low end, but boy, across 20 meters, it's just essentially flat. So this is where the LT Spice simulated the components, and then the Nano VNA verifies essentially what you have. So, you know, 50, 60 bucks, depends where you buy it. That's a worthwhile investment, and it just shows you where our technology is. And, you know, if you didn't have either an Arduino or a Nano VNA, how would you measure exactly what you have and what the result is? So indeed, these are the tools that we have available to us. Okay, next slide. Now, here's the circuit that I'm using for what I call the bidirectional amp and the driver stage. And on the website, I show how you wire up this module so it can be bidirectional. So in one case, the signal is passing from the bandpass filter through the signal transistor stage out to the transmit driver stages, or how the signal passes from your low pass filter antenna TR through the input out to the bandpass filter. So 2 relays enable you to switch this back and forth, and it explains how that works, and you see diagrammatically. So I took this same circuit, and the only thing that I changed a little bit was you'll see R7 is 22 ohms in this case, and that's for the bidirectional amp. And for the driver stage is 4.7. And the reason it's 22, this thing is on all the time, and it needs a heat sink. And I got to tell you, you'll burn your finger if you run it at 4.7 ohms. And that's got to do something to the life of the transistor. So by changing it to 22 ohms, it runs cooler, and it works just fine. But I wanted a little more drive on the transmit side. So the transmit side is only operating you know, sporadically, not all the time as you would have on receive. Now this is working both on transmit and receive, so it's on all the time. So that is 4.7 ohms, and that gives you a little more boost of gain to drive the IRF 510. Next slide. Here is that circuit on a circuit board and the 2 relays, and again, that's single chunk of coax that's kind of running from one relay to the other relay is what enables this circuit to switch the input and output, so that you're either connected to the bandpass filter as an output or connected to the bandpass filter as an input. And this is exactly the same circuit that's used in the transmit driver stage, with the addition or with the difference of a 4.7 ohm versus a 22 ohm. Next slide. And there's a picture, just a slightly different view, but it's the same design. So having a CNC mill, I have this circuit in the computer, and when I want another board, I just punch the start button, and it works very, very well. And I've used this in several transceiver projects recently, and just minimum number of parts, not much to it, and seems to work very, very well. Next slide, please. Here we have, you see on the left is the driver stage, and on the right is the IRF 510. And so I had a piece of aluminum that acts as the heat sink for the IRF 510. And I want to talk a little bit about the IRF 510. Thanks to a trick shown to me by Paul Darlington, M0XPD, he needed 6 volts, matter of fact, for this Plessy circuit, and all he had is a 5-volt regulator. So he lifted the ground connection off of the 5-volt regulator, and he inserted an LED in there, and that raised the voltage above ground by the amount across the LED. And so this is really cool because it does two things. First of, when you transmit and you apply bias to the IRF 510, the light comes on. So when you see the light light up, you know that you got bias juice to the IRF 510. Another interesting factor here is this same IRF 510 circuit can take the Mitsubishi RD06HHF1. Now, the reason that you put that LED in there, normally that's a little 5-volt 3-terminal regulator. Normally about the max you can get out of that is 5 volts. You need a little more than that to bias on the RD06HHF1. You can bump it up almost to 6 volts. And so the thing is, you got to be careful where you got that set, because if you switch between an RD06HHF1 and an IRF 510, if you got the higher voltage on the Mitsubishi, you're not going to hurt it. You put that IRF 510 in there and you smoked it because you smoked the gate. Now, other notable thing about this circuit is, and this was from Allison, KB1GMX, she said, cut the center pin off of the IRF 510 because that center pin is awful close to the gate on the IRF 510. And by cutting that pin, you reduce the possibility of feedback. So you just make the connection. I make the connection there right to the tab because that's the drain connection in addition to the pin. So cut the pin and make a connection up there in the drain. That offers a lot of physical isolation, and that works very, very well. So a couple of little tricks there. And again, this circuit can work either for the IRF 510 or the RD06. Just you got to watch the bias level. That's really important that you keep that in mind. Next slide. Here we have a picture of the backside of the simple SSB, and I happen to have some Uno R3s that I bought when they first kind of hit the market. And matter of fact, a local Radio Shack was selling them kind of at a small discount, and that wasn't a small discount, but I thought that was really great. And they're kind of big because the Nano will do everything that this Uno will do, and it's a lot smaller footprint. So I used what I had. Now, interestingly enough, how I built this assembly, and to the left of the Uno is the SI5351. How I built this is there's a backing plate, and that backing plate is connected to 4 standoffs. And these 4 standoffs are the same mount on the same holes as the LCD. So this whole assembly gets screwed into the front panel, and it's an integral unit. So it makes it kind of nice when you're building stuff that you don't have to say, well, where am I going to put the Uno? In this case, I mounted the Uno right on the back of the LCD, and it mounts to the front panel. And the Plessy bilateral lamps, you see that little arrow there. I used the square island squares. You can see the 4 transistors, and then you see the G-QRP filter. And then either side to the right and left of the Plessy amps are little white squares. That's the ADE ones. Now let me talk a little bit about filters and availability. I mentioned the Model 351 from INRAD. Just a couple of days ago, Wes Hayward, W7ZOI, released a seminal paper on his website about building 9 megahertz crystal filters. And that's quite an excellent treatise, and it tells you how to do it. And that's where, again, the Nano VNA comes in. Once you build it, you can then plot it and make sure you got everything correct. So you have several options. If you can avail yourself of the G-QRP filter, there's not too many of them left, as I understand. The INRAD will work in here, and you just have to match the impedances. And I think if I looked at the paper, the Wes Haywards are 800 ohms. So, and I may be wrong on that, but that seemed to stick in my mind. So you just have to come up with a matching transformer to match to the 50 to the 800. And so that's a 160, 16 to 1. So that's not too hard to match. Anyway, you can see how the circuit all goes together. And I had an interesting problem here, and I want to talk for DFMA. When you build equipment like this, and for those of you who have a manufacturing background, DFMA is designed for manufacturing and assembly. So many times you build rigs and you don't think much about, I may have to do something with that maintenance-wise downstream. Now, on this particular rig on the backside, on the right-hand side, is the bandpass filter. And I put it in there, I tuned it up, and then I found out that there was some interference with the bandpass filter and the side of the case. So you had to go retweak things, and that's kind of hard to do because it's a chicken and an egg. So all I did is I took my Greenlee chassis punch, finally found a use for that 1 1/4 inch, and I just cut a hole in the side of the chassis. So now I have access to screwdrivers, and also it gets the metal away from the bandpass filter. So you need to think about that when you build this stuff. If you ever have to maintain it or test things, can you get really access to it? Next slide, please. The final integration, again, at that website, there's bits of wiring to assemble the modules. You can test as you go. We love to test the audio modules, and that's a real unique test. You hook up the power, hook up the speaker, put your finger on the input. If you get a loud hum, it works. And the LO, BFO, a scope is very helpful to make sure you're getting the right frequency. You need to start with the receiver first and get that working, because there's so many common circuits that if it's working on receive, those common circuits that are working on receive are going to work on transmit. Now, don't be unhappy. It only gets 5 watts of clean power. Some guys have boosted the power up to 8 watts, and the output looks like crap. And, you know, 5 watts, does it, and it's a clean, nice, clean signal with the 5 watts. Next slide, please. Now, I like to think of my rigs as an experimenter's platform, because the modular aspect enables experimentation. Like, gee, I'd like to try a new audio amplifier. Well, if it's all on one single circuit board, kind of hard to do. But if it's an audio module, easy to change. As a matter of fact, the US Ham has built this simple SSB, and he's included full CAT control. So he can do digital modes by hooking it up to his laptop. He has a Nexion touch screen in there. He can actually tune this up and down just by touching the screen, so he doesn't have to touch a knob. He's got a multi-band operation plan and a future AGC add-on. So as I said, I have used this. I have a digital adapter I designed that you just plug into the audio and you plug into the mic jack. And I'm able, using a Raspberry Pi that's got a WSJTX on it, to operate the full Whisper FT8. And this rig has done very, very well. And keep in mind, this is not a kit, but it's also not a toy. And again, the URL for where the detail of how to build this is, you're going to hear this over and over again, but that's where you can find it. Next slide. Now, I have dabbled in some SDR transceivers. I've got about maybe a half a dozen or so, and they've used a little different techniques. Some of them use a Raspberry Pi with a Quist software. And for those of you who are familiar with Charlie Morris ZL2 CTM, he's done it all inside of a Teensy. So I got a couple of those as well. And essentially the SDR radio transceivers with the Pi use an INQ sound card based system, and simple Raspberry Pi 3 computer does all the heavy lifting. The Quist SDR software from Jim Elstrom, N2 ADR, is absolutely superb. And if you look on the right, this is a picture of the spectrum and the waterfall. And the 7-inch HDMI makes it really portable. As a matter of fact, for field day, I took my what I call RADIG. It's a radio in a rig. I took it out to the back patio, and with that screen was working field day operation. It's kind of minimum hardware, not a lot to build it. And there is a website, www.n6QWradiogenius.us, and there's a lot of detail on how to load the Pi and how to load the Quist software and various configurations of SDR. I can tell you, were I asked to do this presentation maybe a year from now, I'd probably be doing nothing but SDR. I mean, the functionalities you get from the dashboard, the filter bandwidth, the agility and being able to switch bands, and just being able to see the signals, see a lot of spectrum. I mean, that's the one short side of the of a hardware-based design, is you can maybe hear somebody two kilohertz away. but with the SDR, you can see at least 48 kilohertz. And I have one sound card that lets me look at 96 kilohertz. So indeed, just depends how much money you spend for a sound card, how much of the spectrum. Of course, DDC is really the way to go, because then you can look at 8 megahertz, not just 98 kilohertz. But there's pretty much minimum hardware, and a lot of the heavy lifting is really being done by the Quist software, which has a whole multitude of bandwidths for sideband and CW, and even receives AM and FM, so it's kind of cool. Next slide, please. Now, these are kind of the last words, and wraps everything up here on the presentation. I want to thank you for the opportunity to present this morning. The build detail, again, is at that URL. And I should also say I've discovered something kind of interesting about hams. You get to talking to them, and you'll find that they have many interests. But it's interesting to note that the second interests tend to be photography. Many are musicians, and a lot of them like to cook. So I'm the cooking guy. I'm not too good of a musician, although I dabble a little bit. But if you go to pastapete.com, you'll see some of my cooking. There's some good recipes in there. So I think it's just something the way we're wired. It's all about home brewing. You're either home brewing photos or home brewing hardware, and or you're building amateur radio equipment. So indeed, if you visit the site, you'll get there's some good recipes in there. I reveal my secret spaghetti sauce, and there's some other recipes that may have some interest to you. So again, these are the last words from N6QW here.
Okay, thanks so much, Pete. That was great. And there's a discussion going on the Q&A page about organizing a Zoom-based build group, and lots of people have chimed in that they'd be interested in doing a module per session and getting together.
Yes.
online. And so for equipment for that, a scope, nano VNA, is that required, you think, or?
Well,
okay.
You can operate in the dark, or you can get a nano VNA. It just gets down to that. Well, the thing is, the cost of the NOV, if I told you to go and spend $5,000, that'd be nuts. But you can
Right.
get something for a lot less than that.
Okay. Let's see if we got some questions. If get my screen up where I can see everything here. Somebody was asking about capacity, sorry, a good source for a bag of good COG capacitors. What are there any better places to get them?
Well,
Other than...
I tend to stick with Mauser and DigiKey and people like that you're going to get reputable parts. When they say they're this, they are that. And the other thing too is I buy in bulk. You'll find many times, you can get 100 resistors for a couple of bucks, or you can get, 100 capacitors for not too much more. So, and the other thing too is, if you look at the designs, tends to be a stock number of parts. For instance, 10 nanofarad, 100 nanofarad, 1 nanofarad, those seem to be the most popular in the bypass. And the resistors, you can go right down the list. You say, okay, I need some 47s, 100s, 220s, 330s, 470s, what have you. For the low pass and band pass filters, you'll find that you need 220s, 470s, some thousands, 330s. So if you buy bagfuls of those, you can build literally any band pass filter or low pass filter. So that works really, really well from that standpoint.
Yeah, you did that on the mentioned that on the podcast a while ago, and I started making a shopping list. I said, okay, rather than okay, I'm down to 3 of these, and I've got all these other values that I don't know when I'm ever going to use from the big kit.
There was a project that appeared in QRP Quarterly called "Let's Build Something," and this was several years ago. And the "Let's Build Something" started off with a direct conversion receiver and then it morphed into a single sideband transceiver. So you started with the DCR, got that working,
Okay.
and we tried really hard to limit the parts and the parts values. So you didn't have to buy, you know, an inordinate amount of, you need one resistor of 2.22K. No, we said you're going to get 2K or 2.7, what have you. So I try to always look for common parts and common part values. And that's the other thing is like 2N3904s. I bought a batch of 100 2N3904s. I paid 4 cents a piece for them on eBay.
Okay. So, and you can keep using them.
That'll buy you a lot of parts.
Right. Okay, we got some questions coming up. Somebody asked about homebrew auto tuners. Let's see. Not many about, but the commercial ones are expensive. Of course, a QRP auto tuner.
Well, that's interesting. You should mention that. Yeah. Well, let me tell you, Bill, who I write along with on the podcast, he's got this thing about analog VFOs and what have you. So I actually bought a really small little servo motor, actually, you know, stepper motor, and I hooked that up to a small little capacitor and say, there, now you can move up into the digital world. You can remotely tune your VFO with the little stepper motor. So then I took that, I have some big capacitors, and I actually came up with a system that you could count the number of turns so you know where you are. It'll show it on an LCD. So you could, there's YouTube videos and have you can build a remote tuner that would do it. So you can set the values or just crank the values in and say, go there, it'll go there.
Okay.
But
have you tried this?
I have done it, but not where where you sense the SWR and then it gives you a feedback loop that says, okay, make those changes.
But as far as a servo motor driving or a
stepper.
Sorry, a stepper driving a tuning capacitor. What do you need a gearbox? What do you do to?
Well, the stepper motor takes care of that. You don't need a gearbox. You just
it's
couple
got enough
the stepper motor to it.
That.
Arduino, and if you look on YouTube, there's 300 videos that I've got, and one of them shows that in operation. You see that thing tuning. Now the other trick was, if you leave the stepper where it is when you shut it off, that's a problem, because if you go tell it to crank in 30 turns, it's going to take it from where it was. So I even came up with a circuit that when you turn it off, it powers itself down and sets it to 0, so that you're always starting for 0. So you can just crank values in there, say 30 here, 50 there, and that'll be. I mean, you might be able to, you know, basically tune those in, note the values down, and say go to 30 and 50. And you can even use relays on a coil to pick the taps that you need if you have like a T-type tuner.
Okay, yeah.
There's a video of that, and there's boards available that interface with the stepper motor to the Arduino.
Okay. We had a question asking about information on how to properly use the Nano VNA. The answer may be go back when we post the archives. There was a great presentation on just that subject this morning, but you may have some more to add to that.
Well, I got to tell you, I had a little problem with the Nano VNA and the Nano Saver circuit. Then someone else it would hang up. And so someone put me onto an alternative. It says, use this. And it doesn't have all the functionality, but it works really well. And I was able to get those plot. You saw the plot of the of that network. And boy, after I got that, I said, whoa, that's really good. As a matter of fact, on the 40 meter network, I had some issues that it had a dip in the middle. So I took some of the fixed value capacitor and put some trimmers in there, so that anyway I could fine tune it. So then what I was able to do is run the 40 meter plot, adjusting the trimmers and run it again. So I ran it to a point where you got it just like the 20 was right on, but the 40 was not that way. It had a dip in the middle. So then I was able to flatten it out. So that's the value of the VNA. You just say, okay, I'm going to tweak these, and then you get a new plot.
That's I got to get one of those. I'm just let's see. As far as I think you touched on this briefly, but those 9 megahertz filters are going to run out. We're not going to have that many. We don't have enough club filters left. What's the best alternative for particularly for a
Well,
club build or
I
something?
tried calling INRAD. Someone actually, the guy who built this simple SSB, and I want to mention about that a minute. He's taking that on as a club project, and he contacted INRAD, and they said for a club, they would give him a discount if he bought enough of them.
Okay.
So that's why I think that they're just available. I tried to call them before this session, but I got no answer yesterday because
Okay.
I thought that would be useful to be able to say, are you going to get some in stock? And it might be this worldwide situation that we're dealing with.
Right.
It's just
Some parts
temporarily.
are just
But
hard
but the 350 ones work really well, and they're about $30. And you can, of course, the new Wes Hayward paper shows you how to hand build those. But the GQRP filters just plunk right in there. And
okay.
I think
Yeah.
I don't think they got that many left. But you
Yeah,
know, don't overlook.
They're gonna be
Yeah,
going.
don't overlook some commercial filters. For instance, you can find a lot of filters out of FT101s floating around, Yaesus.
Okay.
You can get those for 20, $30, and they're 3.180 megahertz. So you just need to adjust your code for
Okay.
different
Oh, okay.
frequency.
So
Yeah, so you can use that for that. So there was also a really great deal out of Israel. They were selling a board with 3 filters on it, upper sideband, lower sideband, and AM for about $30. And you get the whole board with all the parts and everything. And I built a transceiver that instead of switching the BFO is kept constant at 9 megahertz, and you just switch the filter, switch the upper filter in or lower filter. Drake did that. The Drake design was you had a constant BFO frequency at the center frequency. You just switch the filter for upper and lower sideband. So instead of having one filter, you have 2. So you can do that. And I built the transceiver that way, and that works really nice.
Okay. Great idea. Let's see. Sorry, there were some more questions. About a noisy TFT screens. What do you do about? Have you had a problem with noise using those screens, and how do you shield them? And
okay, the TFTs are not a noise problem.
okay,
The
where's it coming from?
OLEDs can be a problem. As a matter of fact,
okay.
I bought a colored OLED, and I built a transceiver that actually appeared recently in the Sprat magazine called the Paisano. I took the Peregrino and I reworked it so that it had as a matter of fact, it has an INRAD filter in that Peregrino. And I found this colored OLED, and I said, this thing is slick because it was small, and it was perfect. What I didn't know is they had a DC to DC converter right on the back of that. When you plug that thing in, it was a noise generator. So the color OLED went away, and I had to go to black and white.
So it's not the OLED. It's just the if you came up with a right,
yeah,
but it's in
right on the back.
there. So you
Integral.
can't. Can you
couldn't
bypass
do
it when
anything
you're
with
on?
it. So I said, okay, forget that. So but now one of them worked. One of the other one I had 2 different models. One of them had the DC to DC converter. The other one didn't. The black and white OLEDs can be noisy, and usually I run a separate supply, and I put a filter network on there. And there's a way to do that. I can look that up. If you email me, I'll dig out the information. But the color TFTs are not a problem.
Okay.
It's only the OLEDs and some of the OLEDs that have the color OLEDs.
And how about the IC2 bus? Is that
no problem?
Okay,
just
that's
plug
not
in.
Okay.
Yeah,
The
only thing you got to know is what the IC2 address is for your specific. Like if you use an LCD, you got to know what that is, because there's usually 3: OX3F, OX27, and OX20, I think. So you got to know. Sometimes you have to play around with those because you get nothing on the LCD.
But as far as noise off of that bus, has that not been an issue?
No.
Okay. Let's see. What is the Dean wants to know? What's the performance difference between an IRF 510 and a Motorola transistor on the final?
Okay, the Mitsubishi is what I've used.
Okay.
Here's what you have. The RD06HHF1. I put it in there because of the problem that you have with the RF510. After 20 meters, the output starts to drop off. I mean, as a matter of fact, the forehands Bidex rig, he'll tell you, microbidex, say, yeah, it's good for 10 watts, but maybe not on 10 meters.
Okay.
So the RD06 is a real RF device, so it has a flat gain over the whole HF band. So if you're going to operate, and with the sunspots improving, you may want to look at 10 meters and 15 and 12. You probably want to put the Mitsubishi. Now, there's about a 10-to-1 price disparity. You can get IRF 510 for 50 cents, or you can get $5 for the RD06. So you can burn up a lot of IRF 510s for 50 cents.
You might have built another radio by the time 10 meters comes back.
Yeah, right, right.
So some people are interested in your graph paper to and what you're using for routing those circuit boards. And a related question: do you ever do any SMT transistors on those routed junctions on the
Yes,
paper?
I have several radios with the SMD. Now, I mentioned the LBS project, the Let's Build Something. That was all built in a big breadboard. I built and that was the subject of another QRP quarterly article where it was iteration number 2 was all surface mount. And I used that circuit, that plus E circuit with the surface mount. And the only thing is you gotta have, if you have FFS, fat finger syndrome, you gotta be really careful what you're doing. You have to have a good arm, good iron, and you gotta be able to hold the parts down steady. So it'll work well, but usually the through hole is a lot simpler to use. And you know, just keep in mind that take your time. Don't be in a hurry. Now, the other problem with a surface mount, and I want to mention this because I ran into this on the second iteration of the LBS, resistor wattage. Most of the surface mount resistors are like eighth watt, 16th watt, 10th watt. And sometimes when you put a 4.7 ohm resistor in a bias circuit, it needs a half watt. And it's really hard to find half watt 4.7 ohm surface mount resistors. So I smoked a couple and I said, boy, that wasn't smart. And the other thing that you have to think a little bit about, and this is the noodling process. If you build something with through hole parts, you always have some place where you can put a scope probe. On a surface mount, sometimes it's pretty hard. And someone told me a trick, which I thought was kind of cool. They said, where you think you're going to make measurements, you take a surface mount like an 01 or 0.1, and you make a tombstone out of it. In other words, you solder it vertically.
So then if you want to make
so if you want a test point, now you got this thing sticking out. It's not connected to anything, only when you put a scope probe on it. And I said, boy, that's smart.
That's great. So we had some questions also about that Teensy SDR project.
Yes,
that's a whole other video.
Yeah. Well, ZL2CTM, Charlie Morris, you can look up his YouTube channel, shows you how to build it. And this is a teensy, matter of fact, what's really, and I haven't done it as yet because of just other things that have been in the queue. The teensy 3.5 is a 120 megahertz clock speed processor versus like 16 with a Arduino and a you know, the various forms of Arduino. The Teensy 4 is a 600 megahertz processor. So if you're doing a lot of number crunching, like the Hilbert transforms, you have to learn the Iowa Hill software to come up with the Hilbert transforms that you put in there that does all the signal processing. But you got a 600 megahertz processor. That thing is cranking away, and it works really, really, really well. And believe it or not, the Teensy 3.5, 3.6 are like near $30. The Teensy 4 is like 19. So I mean, you got a faster speed, less cost.
Right. It
The
doesn't
smaller
have,
footprint.
it's missing some IOs or something. It's a slightly
Well,
different.
you got to buy
interface.
the codec board. There's a
Mhm.
board that it plugs into, and the codec board has the sound part. So that's what
Yeah,
handles
right.
the I and Q, and it's
Mhm.
all an integral assembly. Now, the one thing that I haven't seen, and some people have done this. They can actually. I use typically Charlie's Design currently has LCDs, which work fine, but some guys have taken the color TFT and put the actual spectrum in there. There's a way to take the
Yeah.
FFTs and display it,
Right.
and which is kind of cool. So then you get the spectrum display and the waterfall and everything else. So I mean, lots of opportunity, but it works really well.
Oh.
I've had it on the air, and as a matter of fact, on the website that I've listed for the SDR, you'll see that in operation. So there's a
Mhm.
video embedded in there and shows that. And the guy, you have people tell you what it sounds like or what it doesn't sound like.
Okay, that'd be good. I think I got you off of the previous question about your circuit board router gadget.
Oh, okay.
What's that look like?
All right. My CNC machine costs $250,000. Are you ready for
Okay,
that? $250,000.
$250,000.
Now, yeah, I have a
When you
$250,000
get two.
CNC. Well, here's the story in that. I say it cost me $250,000. My middle son, my youngest son, I should say, is a mechanical engineer.
Mhm.
So he designed and built me a CNC machine, which I have in here, which is really nice to have. And its real cost is $3,000. The $250,000 is what it cost me to send them to school.
Okay, so
That's where the $250,000 came in. So
right.
he builds me this machine, and he shows up with it, and it's about $3,000. And he says, "Here, we're even."
Okay.
You know, we're even. But you can find a really good machine for about $300, $400.
Mhm.
And they're tabletop, and the work area is like about the size of a sheet of paper, which is big enough to build circuit boards. And the
Mhm.
important thing is the G code. Now, if someone has a CNC machine and they have a way of converting DXF files, which is the design system, into G code, then I'll be happy to share with them any of the DXF files. Now, there's a design system free called G Simple.
Mhm.
And G Simple lets you essentially build a whole series of squares, or you can actually draw the circuit out, and then you get a DXF file, and then that's converted to G. I have a converter converts it to G code, and then you just say do that. Now, having a CNC allows you to do kind of interesting things. The one photograph of the KWM4 that I built had a black escutcheon that looks just like the Collins escutcheon. I cut that on a CNC. That's a piece of copper PC board, and then just spray painted it black. So, I mean, you can do all sorts of things. The other thing that's kind of interesting about having G Simple, I mean, you need, whether you have a CNC or not, this is kind of a neat device. I developed some circular dial plates, and I did it in the design, and then I took a screen print and then printed it on photo paper, then just cut it out. So you
Okay.
can make dial plates and things like that just on photo paper, which works really nice. That's the KWM4, and then I put a piece of plastic over the top of it so it doesn't curl up or get damaged. But once you have a design, then it makes it pretty simple. And the other thing is like the ADE1 is surface mount, is all surface mount, and with a G Simple, I just designed a little template and said, okay, cut me an AD1, and it cuts it on a piece of copper. So it's pretty simple. Once you have it, I mean, time to build, take a design and build a board could be as little as 15 minutes.
Wow. Okay. Yeah, that's there are methods to do this with a lot less equipment, but not that fast. That's really
Yeah, yeah.
sweet.
And you have a
I
copy, in the computer. You say, I want another one of these. Boom, there you go.
Oh yeah, right. The duplication is a big advantage over just running it as you go. Um, let's see. Yeah, there was a I don't know, it was on Hackaday or something, but somebody was demonstrating a method where he takes an X-Acto knife, he carves a hook into the back of the blade, and then he just marks off, takes a straight edge, and just rips the copper off and makes a
Yeah.
grid, you know. So less equipment, but not nearly as fast as that. Not
Well, there's another method, and this works quite well. And this is called single-sided copper vector board. You know, the perf board,
hmm
but this has the whole top is covered with copper. So
Okay.
one side is copper, and it's just standard perf board. It's a little expensive, but the thing is, all the holes are 1/10 inch, so you can just drop a socket right in there. And usually, what I do is I have a drill bit. I just go around the holes and take the copper away from the hole, so when you put the socket in there, it's not touching ground. And then you bend your resistors. If it has to go to ground, you just put it through the hole and solder it right to the top of the board. So you got a great ground plane. So you can really
Okay.
rapidly prototype. And I even have cut away copper to make like for a dual gate MOSFET, which has 4 pins. If you take 4 corners and cut the metal away, you have four places you can solder. And you do that with an X-Acto knife and a straight edge. So you can buy that at DigiKey or Mauser. It's a little expensive, but it works really, really well. As a matter of fact, there's a current video on YouTube, my latest video. I built a direct conversion receiver on the top of a piece of that single-sided copper vector board. And it works really, really well. And, you know, you can cut it with a hacksaw, the size you need. And then the ideal part is common copper ground plane. The other thing is if you need to put shielding, you just take a piece of PC board and put it right there vertically and, you know, tack solder it down, and you got a shield around the hardware. So it makes it really kind of nice.
Okay. We're going to have to wrap up in about 2 or 3 minutes here, but
Sure.
got a question from Tristan about, so there are different ADE1 mixers. Do you have any experience with different ones? There's some cheap ones on AliExpress. Are those safe to go with?
Well, I would stick with the ADE1 from Mauser, which in single lots is less than $5.
Okay.
And now they had a crazy pricing scheme. If you bought direct from Mini Circuits Lab, if you bought 3, they were $16 a piece, was $48. If you bought 12, you got the price break, and you could get 12 for $48. So you could either buy 3 for $48, or you could buy 12 for $48. It was the same price, but it was just a quantity buy. And I don't think people realize that. But Mauser sells them at the small price, and I'd stick with Mauser, and I get the ADE1. Now be careful, because there's some versions that don't reach down into the low end of the HF band. Some start at like 400 megahertz to 6 gigahertz. You're gonna miss the HF bands. But the ADE1 is the one that you want that takes you down to the HF. I think it's like 1 megahertz to 3 gigahertz, something like that. So that's the one you want, the ADE1.
Okay. Sounds great. Well, thank you so much, Pete. We've learned an awful lot, and I hope this sounds like we've got enough interest that this module per session Zoom build-a-thon is going to get off the ground.
Well, I just one quick statement here. There was a club in Canada, the Peel Amateur Radio Club, Park. They took on as a project the building of the Let's Build Something, and they broke their club up into groups. And then they had resident experts. So one group was the audio amplifier, one was the balance modulator, and they'd each present each week. But if you had a question about the audio amplifier, you go to the audio amplifier group. So, you know, when you're looking at a group build, if you break it up in segments and you have someone take the specialty, someone that feels comfortable with that part, then you have resident experts. It's not like everybody's fumbling in the dark. You have some people that really know. So I thought that was a really good idea that the Peel Amateur Radio Club had.
Sounds great. All right. Thanks, Pete. Thanks, everybody, for some great questions. Sorry we couldn't get to all of them, but it's been a great session, and we better end it here.
You bet. Be safe. Wear a mask.
Wear a mask.
Social
please.
distance. You bet. 7 3s from the left coast.